It is hard to believe that the most sophisticated devices known to mankind have their humble origins in the most common substance found on Earth: simple sand. But this isn't just any sand. This is the start of an epic journey to refine silicon to its absolute purity, creating the foundation for the AI era. At the molecular level, sand is silicon dioxide. To unlock its potential, we must strip away the oxygen and isolate the pure silicon hidden within its lattice. Inside massive electric arc furnaces reaching 2000 degrees Celsius, the sand is melted and chemically treated to remove impurities through an intense thermal reaction. The heat is unimaginable. In this fiery cauldron, the raw materials are transformed into a metallurgical-grade silicon that is already 98% pure. But 98% is not enough. We need to reach a level of purity that defies imagination, removing almost every single foreign atom from the mixture. We call it 9/9 purity. This means there is only one impurity atom for every billion silicon atoms, making it the purest material ever manufactured by humans. This ultra-pure silicon is the blank canvas for our digital masterpiece. Now, the transformation from raw element to structured crystal can finally begin. Welcome to the world of single crystal growth. Here, we use the Czochralski method to turn molten silicon into a perfectly ordered atomic structure. A tiny seed crystal is lowered into the melt. As it rotates and slowly rises, the molten silicon freezes onto it, following its perfect geometric pattern. Over several days, a massive, heavy cylinder known as an ingot is born. It is a single, continuous crystal, uniform and flawless throughout its entire volume. The ingot is the treasure of the semiconductor industry. Weighing hundreds of kilograms, it contains the potential for millions of individual microchips. Now, this giant crystal must be sliced. A high-speed diamond wire saw, thinner than a human hair, begins the delicate task of cutting the ingot. These thin discs are called wafers. Each one is a precious slice of the silicon crystal, destined to become a platform for billions of transistors. Initially rough from the saw, the wafers undergo a process called chemical mechanical polishing. They are ground down until they are perfectly flat. The surface is now so smooth that any deviation is measured at the atomic level. It is the smoothest surface man can currently create on Earth. Every single wafer must be flawless. A single microscopic scratch or a tiny speck of dust could ruin the complex circuits we are about to build. These wafers are expensive, blank pages of history. They are now ready to be transported to the most controlled environment on the planet. We are leaving the world of heavy industry and entering the realm of the invisible. Precision is no longer a goal, it is an absolute requirement. Welcome to the cleanroom. This facility is 10,000 times cleaner than a hospital operating room, where humans are the main source of contamination. Every person must wear a bunny suit and pass through air showers to ensure not a single skin cell or hair enters the production zone. The room is bathed in yellow light. This isn't for aesthetics. Standard white light contains UV rays that would damage the light-sensitive chemicals we use. The process begins with the application of photoresist. A special light-sensitive liquid is dropped onto the wafer and spun at high speeds to create a uniform layer. This layer is just a few nanometers thick. It acts like photographic film, ready to capture the incredibly detailed patterns of the microprocessor's design. At this scale, a single speck of dust is like a mountain. If it lands on the wafer, it can break a circuit and kill the chip. Every step is monitored with extreme care. The stage is now set for the most difficult and expensive step in the entire manufacturing process. This is the ASML EUV machine, costing over $200 million. It is arguably the most complex machine ever built by the human race. To draw circuits smaller than viruses, we need a special kind of light, extreme ultraviolet light, with a wavelength of only 13.5 nanometers. Inside the machine, a laser strikes a tiny droplet of tin 50,000 times per second, turning it into plasma that emits the precious EUV light. Because EUV light is absorbed by almost everything, including air, the entire process must happen in a perfect vacuum using mirrors instead of lenses. The light reflects off a mask containing the blueprint of the chip, shrinking the image and projecting it down onto the light-sensitive wafer. This is photolithography. We are using light to print the most complex patterns in human history. Layer by layer, with nanometer precision. We are now working at the 3 nanometer scale. At this size, the features are so small that they are approaching the size of individual atoms. To put it in perspective, a human hair is about 80,000 nanometers wide. We are drawing lines thousands of times thinner than that hair. By repeating this process, we can pack tens of billions of transistors onto a single chip, all working together to process data at lightning speed. The machine must align each layer with the one below it within a fraction of a nanometer. It's like aiming a laser at a coin on the moon. A global team of experts is required to keep this miracle of physics running, pushing the boundaries of what is possible in the physical world. Every pulse of light is a step forward for human civilization, embedding the power of computation into a piece of refined sand. These are the smallest structures ever mass-produced. They are the switches that turn on and off to create the ones and zeros of our digital life. The pattern is now set, but the drawing is only the beginning. Now we must turn these patterns into physical structures through chemical warfare. Next comes the etching. We use reactive gases and plasma to physically carve away the silicon where the light didn't reach, creating deep trenches. This is chemical carving at the atomic scale. The photoresist protects the circuit pattern, while the plasma eats away the exposed silicon with surgical precision. Now we must change the electrical properties of the silicon. In a process called ion implantation, we fire high-energy ions into the crystal structure. These foreign atoms allow the silicon to conduct electricity under certain conditions. This is what makes it a semiconductor, the heart of all electronics. After the ions are in place, the wafer is heated in a process called annealing. This repairs any damage to the crystal and locks the atoms in place. To connect the billions of transistors, we need wiring. We use electroplating to deposit a thin layer of copper into the etched trenches of the chip. This creates the circulatory system of the chip. Miles of microscopic copper wiring are packed into an area no larger than a postage stamp. We polish the surface flat again and repeat the process. A modern chip can have over 15 layers of copper wiring stacked on top of each other. We are building a vertical city of logic. Each layer is connected to the one below it by tiny vertical pillars called vias, creating a 3D structure. This architecture is the most complex thing ever designed by humans. It is a labyrinth of billions of switches, all precisely synchronized to work together. The chemistry must be perfect. Even a few stray molecules could increase electrical resistance and slow down the entire processor's performance. These pathways are the highways of the digital world, carrying the pulses of light and energy that define our modern existence and future. The production process takes months. A single wafer will travel through hundreds of machines and undergo thousands of steps before it is finally finished. Now, the moment of truth. After months of work, we must find out if the circuits we built actually work as they were intended. This is the wafer sort. An array of incredibly fine needles touches the contact points of each individual chip to test its electrical signals. Each chip is tested. In a world of nanometers, not every chip is perfect. The machine identifies and marks the ones that didn't make the cut. Once testing is complete, the wafer is diced. A precision saw cuts along the grid lines, separating the wafer into hundreds of individual dies. These dies are incredibly fragile. A robotic arm carefully picks up each working chip and places it into its final protective housing, called a package. In the packaging stage, we connect the chip's internal wiring to the outside world using gold wires or tiny solder bumps that act as connectors. A protective layer of plastic or ceramic is added to seal the chip away from the environment, protecting it from heat, moisture, and physical damage. Finally, the chip receives its identity. A laser etches the manufacturer's name and the model number, marking it as a completed piece of technology. From a single grain of sand to a high-performance processor, these chips are now ready to be shipped to factories all around the world. Only the best survive this journey. These silicon warriors are the result of thousands of hours of engineering and the peak of human ingenuity. Whether it's in a smartphone, a supercomputer, or a car, This chip is now the brain that will drive the functions of our digital lives. Thousands of these chips work together in data centers, processing the vast amounts of information that power the internet and the global economy. Our modern cities are living, breathing networks of silicon. Every traffic light, every financial transaction, and every communication depends on these tiny devices. And now, these chips are enabling the birth of artificial intelligence, allowing machines to learn, reason, and solve problems that were once impossible for humans. From medicine to space exploration, the power of the semiconductor is extending human capabilities beyond our biological limits, saving lives and exploring new worlds. The future is being written in silicon. Every advancement we make as a species is now intrinsically linked to our ability to craft these micro-miracles. We often take it for granted, but every time we touch a screen, we are interacting with the culmination of decades of scientific breakthroughs. This tiny piece of material is the most powerful tool ever created. It is the bridge between the physical world and the digital infinite. We have turned the Earth itself, in the form of sand, into a global brain that never sleeps, connecting billions of people across the planet. It is a journey of transformation, from a humble grain of sand to the high-tech heart of the modern world, driven by human curiosity and passion. Silicon is the material that changed our destiny. It is the foundation of our present and the architect of our digital future for generations to come. As we look to the stars and the next frontier of AI, remember that it all started with a simple, quiet grain of sand on a beach.